Good morning, sir.
Good morning, all of you. Today we are going to start. Last class we basically discussed on the polarization, how to create a linearly polarized wave, how to create this elliptical, how to create the circular polarized wave. We also discussed about different superpositions. Okay, so today because we need the propagation of electromagnetic wave in an isotropic medium, so we need to understand the phenomenon of displacements. It is basically mu, and it is basically measured in hertz. And permittivity, we basically know that this is E0, or you can call it ER. Okay, so basic meaning of permittivity is how the medium allows electrical interaction. So that is the basic meaning of permittivity. Since we are dealing with electromagnetic wave, basically we'll see that how this electromagnetic propagates in the medium. So we'll basically see how electric vector and magnetic vector propagates in a medium. Okay, so now let me give you some basics about the refractive index. So first of all, this refractive index is basically speed of light, and this is divided by speed in the medium. And what we call is like N is basically C by V, or we basically another way we call it like optical density. This is the basic definition of a refractive index, means how this light is basically propagating through different media. We are going to deal with a different kind of medium like isotropic, anisotropic. That's why we need this. And since electromagnetic waves, they have different frequencies, so we need this refractive index. So let me, yeah. So now what we are going to do, we are going to study. So aim is we need to study refractive index as a function of frequency. So that is our main aim. Okay, so what we call, we basically define refractive index. There are different formulas. So definition of n. So we have different formulas. So the first formula is your C by V. This is your N is equal to C by V. So this is your fast formula. Next formula is N is equal to epsilon mu divided by epsilon 0 mu 0. This is for any medium. Next, we have refractive index, basically for dielectric medium. So this is basically only for dielectric medium. So this is 3. This is for dielectric medium. Next, we have another formula that we basically call Cauchy's formula, which is basically N is equal to A plus B by lambda, then B by lambda square plus C by lambda to the power 4. This is called Cauchy's formula. And another we have, so if we are traveling in any medium, basically the wavelength basically changes by refractive index amount. So Let me write down, this is lambda 0. So lambda 0 is the wavelength in free space. So these are all the formulas are available to us regarding refractive index. The first formula is basically C by V. So basically the velocity is reduced in a medium. Second thing is this is C is basically because C is basically 1 by epsilon 0 mu 0. This formula we have applied here to get this. So for any medium, this is applicable. Now for only non-magnetic dielectric medium, this formula is applicable. And this is a Cauchy's formula. This is empirical. This is experimental. So this is one of the formula we use basically for refractive index. Now the major thing is we need to study the variation of refractive index as a function of frequency. So what actually happens? Let me write down that. Let me write down this person. Okay, so this is a very important concept. So when electromagnetic wave basically travels in a medium, different waves travel with different speed. So I would like to write that when EM wave travel in a medium, different frequencies travel with different speed, right? This phenomena, this is called dispersion. Is it clear?
Yes, sir.
So the properties when electromagnetic wave they travel means there are, suppose you take a case of light. So you take example of light. So this is light. So 7 colors we have. So that means 7 frequencies. That means 7 different speeds. So all the colors they will travel in a different speed. So if you have a blue light, it has basically high energy, so it will travel faster, and it has depends on the frequency or wavelength, whichever you choose. So different frequencies they travel with different speed. This is the phenomenon of dispersion. So this is a very important concept. So I would like to draw that graph how. Uh, So this is one of the example you must understand. So you can see that if wavelength basically increases, refractive index, this is in the higher angstrom side. Okay, so higher wavelengths they have low refractive index, and this is basically n is inversely proportional to 1 by lambda, which is actually Cauchy's formula. So this is one of the example. This is actually in GATE or NET in JAM. They basically ask this question: how refractive index varies with frequency or wavelength, and what formula that name is. So this is experimental law. Okay. So next, okay. Next we need to, because so phase velocity. Okay. So what is the meaning of a phase velocity? When many waves or many EM waves, I'll write many waves travel in a medium. Let me take example here. Example is light, white light, right? White light. So white. So there are 7 frequencies. So many electromagnetic waves travel in the medium. What happens? The velocity of individual wave is called phase velocity. Now it is a very important concept. So I am having frequency mu, basically from white light means, so white light. So I am having frequency basically 400 nanometer to 700 nanometer. Okay, light coming from sun, from sun. So that is also having frequencies from mu is equal to 0 to infinite. No, it is very big range. Range is big. So from sun, all frequencies are coming for white light, 400 nanometer to 700 nanometer. What I'm trying to say is individual wave means this white light. You have red. Red, the velocity of red, it is basically called a phase velocity. The individual component is called phase velocity. Now, what will happen when different frequencies, because it is white light, so there are different frequencies. So when different frequencies travel in a medium, they superpose to form what they form. So superposition is basically 3 types. I'm writing it here. So let me do 1 second. So superposition is basically 3 types. So one is interference, one is beats, one is stationary wave. So what I'm asking here, when different frequencies travel in a medium like light having 7 colors traveling in glass or air or in water, they superpose to form what? What they superpose to form? Which of the phenomena? Interference, beats, or stationary wave? So this is different frequencies. Can anyone tell me?
The beats.
Yeah, this is beats. Very good. So what will happen? So the total amplitude is basically 0 to infinite. I take the many frequencies. So 1 by 2 pi. So this is, let me add the guest. Okay. So can you tell me this formula what I'm writing? Just have a look. This is the actually large scale form of the bits. Means it is the common way to write bits. So f of k. So this is 1 by 2 pi 0 to infinity e of x, or e of xt I'll write, e of xt, e of xt e to the power I k x dx minus. So what I am trying to do is I am going to superpose each of the electric wave in the medium in the range from 0 to infinite, and this is variable of k, means k is 2 pi by lambda. So what this expression is known as? Can you tell me what is the name of this equation? Can you tell me?
No, sir. No.
So this is Fourier transform.
Okay. Okay.
Actually, Fourier transform is nothing but addition of all the different frequency. I am writing it here. So here f of k is basically addition or superposition of E1, E2, E3 like this. Okay. So now the shape of the curve. So previously, this was like individual waves. So this is one phase wave, that is another phase wave. Then we have different phase waves. So this is one, this is two, this is three. What they will do whenever they try to travel in a medium combinedly, they actually form a group wave. Okay. So actually they form a group wave, and these individual waves are inside the group. So this is called a group wave. And the velocity is basically written as, so phase velocity is basically v is equal to c by n. You can write it is the phase velocity, and or you can write omega by k, because it is individual property. Okay. And this is group velocity is Vg. So this is d omega by dk. So this is group property. So I repeat again. So whenever we have different waves traveling in a medium, they travel with different speeds, or they travel with different frequencies. So whenever different frequencies they travel, they form the basically the beats phenomena. In a beats phenomena, what will happen? Different waves, the individual waves or the phase waves, they combine to form a group. This envelope is called the group velocity, and all the time Vg is less than Vp. So Vp may be very high, but the group velocity is very, very small. Any doubt or anything you'd like to ask?
Sir, this type of phenomena is exclusive to light, or we can also create this by electrical signals.
This is valid for any wave.
So can we recreate it in lab with electrical signals, with different electrical signals adding?
Yes. Actually, I think sir was doing on practical, right? You are combining two waves in. So what you can do, you can try different frequencies. You can apply if you have different, different input connector. So you can connect 5 to 6 waves at a single time, allow them to travel in the same direction with different frequency, and you can easily see this group wave, this wave packet. You can see that, and this is a property of, means, any wave. It may be matter wave, it may be pressure wave, it may be sound, it may be longitudinal, it may be transverse, whatever that may be. It is valid for all the waves, because beat
Sir,
is a phenomenon.
so is this the quanta, like what we talk about in light, or quanta?
Yes. Actually, it is the wave, means, what do you call? No, this is actually that thing. Means, you write, no, E is equal to h mu, or E is equal to n h mu, or P is equal to h cross k, right? So this h nu, this actually the wave packet is called quantum. This wave packet is called this wave packet is called quantum of light. This is the smallest possible, but the thing is, you have to make sure they basically go from 0 to infinite, e xt e to the power minus ikx dx. So this has to be, see, two waves are there. What is the size of a sine wave? Sine wave basically spreads from minus infinite to plus infinite. Then if you add another wave, it will reduce its size. At the end, this graph, if you add many waves, so the size of the wave packet will be like, it is very small. The dimension will be very small. Okay, so delta x is very small, and this is called a packet. Is it clear?
Yes, sir. So another one. What is the difference? Like, what are the conditions for different type of superpositions? Like, how can we get difference from beats to interference or stationary waves?
Okay, I'm writing that. So we have superposition. So I'm writing the technical definition of superposition. Waves, waves superpose at x and t simultaneously. So these are waves, so they can superpose. Okay. Now superposition is basically addition of waves. I can go for a vector addition. So this is a vector addition. So now these are three types. Three types means interference, then beats, then we have stationary wave. So interference means two waves traveling in same direction. This is important. And identical slash same frequency and in phase. Coherent waves, you call coherent waves, right? So in beats, two waves traveling same direction. Second is different frequencies. Third is two waves traveling in opposite direction. Same frequency. Is it clear?
Sir, for interference, is it necessary that the both should be in same phase?
Actually, phase conditions come out due to this destructive and constructive interference. I can still remove it. There is not a mandatory thing here. I can still remove it. Okay.
Yes, sir.
So examples are interferences. You know this Young's double slit model. Beats. You know this matter wave or group velocity, phase velocity. Stationary wave is basically vibration in a string. So what happens when basically you vibrate? You make two sides fixed. So you make two sides fixed. Basically, they actually vibrate in this, right? Or they can vibrate in like this. It depends which of the tone they basically prefer. Is it clear?
Yes, sir.
Okay. So now we are going to enter. Okay, we completed up to this group velocity and phase velocity. Then we are going to do. I think I should paste this picture. So this is one of the image you can see, right? So this is group velocity, this is the phase velocity. So individual wave inside the group is called phase and the total group is called group. Now, okay. So why these things are happening, we are going to do a mathematical, rigorous mathematics on that. So let me write down first. We will go for system. So EM waves traveling inside medium. This is my first step, right? Next is medium contains Let me write down this, not this one. EM wave is electric field okay. That means electric field means it is actually force, and this force is oscillatory. So means force. So when electromagnetic waves travel inside a medium, actually there is a force. This force acts on atoms and electrons. Okay. Now, next thing is electrons or atoms. They are actually connected. They are spring mass system. So spring mass system means there will be a force called F of x attached to the electron, and you are actually applying a oscillatory force to this spring mass system, right? So this one I can write k is equal to m omega square. Here m is basically mass of the electron, omega is the frequency of vibration. I can write m omega square x. This is nothing but spring force, right? So whenever, let me draw an image. So this is my material, and the electromagnetic wave is traveling like this, and this is my atom. I'll change a different color. So this is positive, this is negative. So what actually happens when electromagnetic wave or force basically travels the medium? It actually vibrates. It actually make a forced vibration, vibrates the atom or electron, or in conclusion charge particle. Okay, so this charge particle, they form a oscillatory motion. So now I am going to write down the basic formalism. So this is one of the equations we must understand. So this is actually the electron. So electron is basically in a system. It is attached to some new central force. So it is actually, you know, some spring mass system, because it is like a dipole. So when electric field is there, so electron basically vibrates. Okay. So I'll write it. So in conclusion, when EM wave travels in a medium, electron vibrates. Is it clear up to this point?
Yes, sir.
Next is, we should write the equation of motion. So this vibration, there is also called damping. So this, due to the vibration, some damping will be happening, and that damping is basically this damping, because
Sir,
it is
what,
vibrate.
which part of the, like, what causes the damping in this?
Okay. So damping is basically this electron is vibrating, right?
Yes, sir.
So what will happen? There are other nearby electrons, right? So they try to interact with each other, because electron is not a single electron inside the material. It is connected to a positive charge, to a negative charge, right? It is maybe valency, it may be, you know, open. So what will happen? The other things will also interact with this, and they will try to reduce the velocity the way the external field is applied. Okay.
Okay, sir.
So this damping is due to the nearby interaction. So they try to reduce the velocity. So that's why this damping force is always proportional to velocity. Remember this. So damping force is always proportional to velocity. It is important. Okay. So this is one, and we have a driving force. This is electromagnetic force. So I'll write it. So this is the driving force. This is the external force due to electromagnetic wave. So external. Okay. Now we'll write the equation of motion. So equation of motion is this one.
So why did we remove the x part of the equation in this case?
What I removed.
From the force, it's a function of t only. Why we remove the kx part?
It is there. It is binding energy is there.
Okay, okay.
So this is actually m omega square x, right?
No, sir, I
And
was
this
talking
is
about the driving force.
driving force is there. No, it is there.
No,
It
no,
is there.
no. We wrote that force q e naught of sine omega t minus kx, right? Why we remove
Yeah,
the
this no, no, this is there. This is there. This is there. This is there. It is the external force. It is external.
so the external force is the driving force, right?
Right, right. External force. It is like a forced vibration. No, suppose you the volleyball player, they often used to put the ball on the ground and they often slap it. Right? They do like this. Right? So that is the external
Yes,
force because this is the periodic force.
yes.
Okay. So the total force acting on electron. So this is total force acting on charge. So this charge may be anything, right? Electron, atom, ion. So this is a binding force. This is basically F is equal to Kx. This is the damping force. This is due to the interaction on the neighboring part, and this is the driving force. Means it is the external force. So the total force is equal to mass into acceleration. So this is the equation of motion. Is it clear about this equation?
Yes, sir.
Next is uh, we'll write this in this format. So now it is coming in x variable. So this is which order differential equation?
Second order.
Second order linear. This is non-homogeneous, and this second order linear non-homogeneous, and this is ordinary. Ordinary and partial differential equation. Okay. So here m is mass of electron, x is the displacement, t is time, gamma is damping, E0 is the electric field, omega is the way which we vibrate the electric field, means of the electromagnetic wave, q is the charge. Is it clear?
Yes, sir.
Okay.
So can you
So
wait a
now,
little bit?
yeah, I'll
Few
wait.
minutes.
If you have any problem, then tell me. I'll share this PDF copy also, means after this class.
No, so just 2 minutes. I'll finish it.
Is okay. Okay. So next is, this is a differential equation. What it says that there is a change in position of the electron as a function of time, and we are having, this is due to the binding force, this is due to the damping force, and this is due to the oscillatory force. This is the change in the position. Okay. So this is the second order differential equation. Now, if you do that, we can write this wave in form of this one. I have not done anything, just I have used a oscillatory form. So in terms of sine kx omega t, I have just go for oscillatory term. Is it okay?
Yes, sir.
Only the change some पैरामीटर्स इधर उधर किया और कुछ नहीं, सिर्फ इसको e to y omega t कर दिया क्योंकि इलेक्ट्रोमैग्नेटिक वेव है. Nothing I have changed. And this kind of system, they have a solution of this form. So this is the solution. So what actually this solution tells me is that how the electron is vibrating, how the electron's position changes with time, right? Basically, this is the position, this is the time. So how the position basically changes time, and it says this will basically some oscillatory form, right? So this is basically the solution. Okay. Next thing is okay. And if we put this solution inside the differential equation, this will give me this form. Put solution in this equation. This is x, I write in x. So you will get this much. Okay. So this is the solution. Basically, this is the amplitude. Because this is the solution, and here if we put that, we can calculate this one. Okay, the one. What it says is that the amplitude depends how much electron will vibrate, because we are allowing the electromagnetic field to enter in a medium. Electric field has some force, so the force will vibrate the electron, and how much that vibration basically depends. It depends on charge, mass, external, and we have damping. Okay, so this is charge, this is mass, this is external frequency, and this is damping. This is very obvious that the external this amplitude of the electron motion vibration is basically depends on this thing. Okay, so this is actually the driving, and omega 0 is the natural frequency of vibration. Natural frequency of electron. Okay, vibration of electron. Is it clear?
Yes, sir.
So next, because this is actually an electron, so if I multiply with charge, this is the displacement. If I multiply with the charge, then what I'm going to get? This is the thing. So if I multiply with a charge, so this is displacement multiplied with charge. So this is charge. So what is the value we are going to get? We are going to get dipole moment. So now the electron is having a dipole moment which has of this form. This is the total form. This is the amplitude part. This is the x0 amplitude part, and this is the oscillatory part. So this is oscillatory. Is it clear?
Yes, sir.
So next is, so I am just, because there are n number of electrons, I am just going to write a general expressions now. So because there are n electrons, so this is for a single electron. For n electrons or for medium, what we can write is, we can write this expression. This is for actually a better expression for a medium. Okay, this is similar, but for this is for single, but this is for large. So J basically for each kind of electron, or we call it oscillator. So J basically is called a oscillator. Oscillator number, okay, and N is basically number of oscillators. This above equation has just been go for a large number of things, so summation is there. So this is for N oscillators. Is it clear?
Yes, sir.
So what actually we are thinking is that this equation is basically of this form like this. This P is of the form like this. Okay. So you can see there is P, there is E. There is P, there is E. Whatever the things inside, we just included inside this. Where you have seen this equation? You have seen this equation in dielectrics, where polarization is proportional to the electric field, and this is for linear medium. Is it clear?
Yes, sir.
And we can write this epsilon constant. So the dielectric constant we can write from the above equation. Just this is just the total, right? So this is basically the dielectric constant because P is equal to epsilon 0 E. So this it will come like this because susceptibility is basically 1 by dielectric constant. So this one is there. That's the reason. So this is complex dielectric. DE is constant. So complex dielectric constant is again N is basically ER. You understand my point now, right?
Yes, sir.
So here the dielectric constant is basically proportional to this all parameters. This is the amplitude parameter. This is related to oscillator, charge, number of oscillator, mass of the electron. Actually, refractive index is proportional to so many terms. So for isotropic medium, it is okay. But for non-isotropic medium, it is very complicated. Yes, the way we take like N is equal to C by V, it is not that easy. This is very simplified. Actually, this behaves in this format. So this is the way actually the refractive index behaves in a medium. It depends on the mass of the electron, it depends on number of oscillator, it depends on the charge, it depends on amplitude, and it depends on the individual frequency, it depends on damping, it depends on the external frequency, it depends on many things. So it is not a simple thing. For linear dielectrics, it is fine. But for anisotropic medium, the relation is complicated. So for polarization, what we are actually need is that the electromagnetic wave is traveling in a anisotropic medium, and we are going to use this kind of formulas. Okay, so what will happen? I'm just going. I think. So this is actually the formula for refractive index for a dielectric medium. You can also convert for this in a metallic medium also. Okay, so I'll just write one thing. Uh, have you seen this graph? Have you seen this graph? Where you have seen this kind of graph?
Sir, don't know.
Actually, this is basically a concept of resonance. Okay, so this is actually resonance concept. So what happens when external field is actually because atoms they vibrate basically they have distance like angstrom order, so they basically vibrate in IR range like 1 electron volt to 2 electron volt energy. So what happens when electromagnetic wave is falling on them, these electrons they have their natural oscillations, right? So whenever their natural oscillations is matching with the external oscillation, there is actually a there is actually a change of phase, and there is actually a resonance. This is actually the picture of the resonance when the external when external omega of EM wave is equal to the oscillation uh, omega of the individual oscillator. Then what happens? Resonance happens. And this is valid for ionic polarization. This because this is ionic polarization. It is dealing with electrons attached to the atom, so it is ionic polarization. Electronic polarization is there, so this is one kind of resonance. Okay. So this is whenever applied frequency matches with the individual, so you have resonance unless you just go through a step out call. Okay. Is there any doubt you can ask me?
No, sir.
So this one I have taken the reference from Griffith book, and the page number is let me check it out. Page number is what is the page? 417. So this one I have taken Griffith book. The reference is Griffith book, page. This is pages 417. So if you have any problem in the equations, you can see it there. So this is all about dispersion, how this electromagnetic wave travels in a medium, and how this refractive index is a complicated formula, rather simple formula. What you study, it is actually really complicated formula. So you have to be very careful while using the refractive index, because this is of this form rather than this is not actually correct. Means it is a very simplified, means overstated thing, right? So this is all about today's class. So anything you like to ask, you can ask me, and that's all for today's class. So let me close it, stop the recording.